Hi, this is Jose Luis, and welcome to another video on the series Introduction to Parametric Modeling. In my previous videos, I have discussed how to create and modify vectors and how to work with planes. But if you think about them in a super abstract way, what they basically are is just collections of numbers. Point and vectors are 3 numbers if you have them in 3D space, and then planes are basically 9 numbers, the numbers that define the origin and the 2 vectors that define the orientation. So it turns out that numerically they are very simple to represent, and it turns out that in order to generate sequences of points, of vectors, and of planes as well, it is actually very handy to get a grasp on how to generate series of numbers. So in this video, what I would like to teach you is how to generate a complex series of numbers using Grasshopper, for example. And we're going to see 3 main things. We're going to see how to create domains, how to create series, and how to create ranges. What does that look like? Well, we're going to start with domains. We've actually seen this in a previous video, but if you go to mathematics and if you go to domain, you can see that there is this entire category that is about domains. Domains in Grasshopper world is basically an interval defined by a starting value and an ending value. It's just as simple as that. It's 2 numbers that define a start and an end. And this is very useful because sometimes when we create geometry, for example, the size of a rectangle or the diameter of the size of a cube, instead of defining it in size terms, we define it in domain terms so that the object can be offset from the center point. We've seen this before. Constructing a domain is just as simple as giving it a starting point and an end point. So for example, I'm going to drop here a slider that starts at 10, but I'm going to right click and I'm going to make sure that the starting value is -10 so that I can have positive and negative values. So I'm going to call this start, and then I'm going to copy and paste this, and I'm going to call this the end. All right. So this domain is going to start, for example, in -10 and it's going to end at +10. And if I plug in here, a panel, you can see that what it says here is that this object that is coming out of here is a domain that starts at minus whatever or positive whatever to the other value. So -10 to +10. All right. You will see very often in Grasshopper components that ask you for domains. So for example, as I said, if we want to create a rectangle, what is the rectangle? You can see that the rectangle in the x direction is asking for the dimensions as a domain so that it knows how to offset or how to center this object in the plane that is the base for the rectangle. All right, so this is just a simple domain, and sometimes it's called an interval, and the 2 numerical extremes that define this domain. But I may actually want to generate more complex series of numbers. I may want to create sequences of numbers that start at a particular value, that end at a particular value, or that have a particular amount of numbers and a particular distance between them. This is also very useful. It will be very useful, for example, for creating, I don't know, sequences of points in 3D space, which I think is an example that we're going to do in this video. So for example, let's say that I go to the Sets tab and I click on Sequence. If I click on Sequence, you can see that there is a component here that is called Series, and it's useful for creating a series of numbers, just as simple as that. The inputs are going to be S, the starting number, and the step size, and then C is going to be the number of values in the series. So I'm going to copy this and I'm going to say this is the starting value, which I'm going to set at 0. I'm going to copy this and this is going to be the step size. And then this C is going to be the number of values. This has to be an integer. So I'm just going to say, for example, 25 values or 10. And then, for example, if I click here, number 1, and then I type count, and it's going to be C. Then what you can see is that the output is a list of numbers that starts with the starting value. You see? The step size is 1 unit, and there are 10 numbers on this list. I can choose to have more or less values. I can choose to change the starting value, and I can choose to increase the step size or to decrease the step size. The step size being the interval, the gap between these numbers. So numeric series in Grasshopper is a way of creating series if you know what is the starting value and if you know what is the step between values. All right, this is very important. And it's very important because it's different from the other way that we have in Grasshopper of creating numerical series, which is using ranges. Ranges is a very, very similar concept, but it's slightly different in that instead of defining the beginning and the step size between values, what we define is the beginning, the end, using a domain, and then we define how many intervals we want in between. So for example, let's say that I choose to start at let's say that I look at the value, I look at the range, sorry, and you see that the input is asking me for a domain. So it's asking me if I want values between -10 and +10 in this case. And n is asking me for the number of steps between values, which is going to be also something. So for example, here I'm going to rename this to steps. And then I'm going to plug this in here, and you're going to see that the result of this is going to be this much. So it's a sequence of points that go from -10 to +10, and there are 10 steps in this series. All right? Now, I want to highlight one thing that is typically a little confusing, but that we need to wrap our heads around. Let's say that I said that the starting value was going to be the value of 0, the end value, the value of 10, and 10 steps on the series. Look at, which is basically trying to mimic what I did here with the series. What's interesting is that if I compare the results, it turns out that the range is giving me one more value than the series. And it is so because what I get with range is that the number of the input that is asking me for is the number of steps, as opposed to series, which is asking me for the number of values in the series. If I divide a domain, for example, in 2 steps, then what I get is 3 numbers, the beginning, the middle, and the end. If I divide it in 3 steps, I get 4 numbers. If I divide it in 10 steps, I get 11 values, which is what I have here. Because remember, index numbers, I start counting with 0. So 10 as the last one means there's 11 values. So keep in mind that when we use series, we want the amount of numbers of values, whereas when we use range, we specify the amount of steps in between the values. And therefore, the amount of values will be the amount of steps plus 1. Okay, let's keep that in mind. Now, why is this useful, Jose? This is kind of boring. We're just generating numbers after the other, right? Duh. Well, it turns out that having this fine control on the generation of our numerical series is actually really helpful whenever we want to use this information to generate sequences of geometry as well. So for example, let's see a really simple example of how to generate a 1D, one dimension array of points. So like a sequence of points, one after the other. So the way we have seen how to generate points in the past has been using the construct point, okay? And the way we typically did that was by saying, I'm going to work with the coordinate x, the coordinate, and then the coordinate y, and the coordinate z. Okay, and that gives us a point that we can use to control in 3D. All right? But what if instead of just plugging in here one single value, what if we plugged in a list of values? How would that work? Well, let's see if we can make that happen. So I'm going to copy paste this series. Okay. I'm going to bring it all the way down here. And then what I'm going to do is that the x coordinate, I'm going to detach it. So I'm going to right click on the component here. We haven't seen this yet. And I'm going to, well, you can't see it, sorry. I'm going to right click and I'm going to disconnect the first slider that is coming in. So that slider there. And then what I'm going to do is I'm going to, because I like visualizing things, I'm going to make sure that I have a panel here. So instead of plugging in just one number for the x, what I'm going to do is I'm going to plug in a series of numbers. And then what happens is that, remember, the component works when components combine data. What they do is that they perform every operation by matching objects one to one. So what we get in result is a collection of points that have all these x, y, all these x components, the series, and then the y and the z are the same, which are these hard-coded values. If instead of x, I wanted to do that in the y direction, I could just plug this one in here and then plug this one in here, and now the points are going in the y direction. Or if I wanted to do that in the, I wanted to do that here in the z direction, so now the points are going up. Okay? So now I can generate one-dimensional series of points. Now this is kind of interesting because then it opens up the possibility for a lot of creativity. Because, for example, what if instead of having these points just be boring, like, just instead of being boring a straight line, what if I wanted to do something a bit more creative? Something I could do, for example, is I could create a series of points that is kind of undulating like this. The way I can do that is by by working with these points and then giving them an x coordinate that is growing in this direction, but then give them a z coordinate that is undulating and is oscillating between the values of 0, 1, and -1. I can do that with a sine function. So for example, let's say that I'm going to change my series, or I'm going to create a new series instead. Okay, it's going to start, or I'm going to do it with a range instead. Actually, now that we're talking about it, I'm going to copy this range. Okay, and I'm going to say that the range needs to start at 0. The range needs to end at 307 needs to end at 720, which is 2 times 360, so 2 iterations. And then the amount of steps is going to be 1 minus the count here. So that's going to be subtraction. So that's going to be 10 minus 1. And I'm going to hard code that so that the numbers match. So this is -1, and then this is going to be here. So what I have done here now is I have created 10 numbers. Sorry, it's -1, so it has to be +1. So I have created 10 values that go from 0 to 300 to 720. If I use those values now as the z coordinate, you can see that what I get is like this really sharp straight line that is like slightly inclined. But what I want to do is I want to make sure that instead of that, what I want to do is I want to use that to create some kind of like undulating effect. So what I can do is I can calculate the sine of this value. So I can go to mathematics, trigonometry, and calculate the sine of this value. And if I do that, I can plug this in here, and then I'm going to get very strange results like these ones, just because the sine function by default works with radians, and here I'm working with degrees. So there's actually a function here that takes an angle specified in radians and turns it into degrees. Or, so I could do that, and now I have the, oops, sorry, actually the other way around. I have to turn the angles in degrees into radians. So I can do that, and now my angles are specified in radians, so 4 pi. And then if I feed that to the sine, you can see that now it's a little better because it's 0, blah, 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 and then it oscillates back into 0. And then if I plug that into C, you can see that I start getting this kind of undulating effect. If I crank the count of points up, so you will be able to see that I get a much nicer definition. You see, I get a much nicer definition, and I can squeeze that in here, and I get this like nice undulating curve, which it is made out of points. It's just a sequence of points. And you can see how here I have all the points from -1 to 1, all the C coordinates. This can now, all these points, I can use them to create, for example, an interpolated curve. All right. And this interpolated curve, if I turn off the points, is roughly following the shape of a sine function, as you can see, which is also kind of nice. Woohoo! Now, something that I can also do, for example, is I can use numerical series to create a circle, of points, right? How does that work? Well, if I want to create a circle that ends up in a circle, what I need to do is basically I want to be able to create a series where what I want to do is I want to be able to say I'm going to create a series where I'm going to start with this angle, and then this angle, and then this angle, and then this angle. And for each value of these angles, I need to find the x and y coordinate of this point. And it turns out that if you refresh a little bit of your trigonometry, I'm not going to do it right now here, but I might do it in some other video. If you refresh a little bit of your trigonometry, you can see that this forms a triangle that is a square here that has 90 degrees. And then the x coordinate of this point equals this distance. And with trigonometry, we know that the x coordinate is going to be equal to the radius, which is going to be this one here, times the cosine of the angle, which is going to be this one here. And so that's going to be x. And we also know that the coordinate y, if you refresh a little bit of your trigonometry again, we know that the coordinate of y is going to be the radius, which is that distance, times the sine of the angle that we are forming there. So if I create a series of angles that go from 0 to 360, and I can use that to compute the x and the y, and then use those two values to compute the circle. All right, let's take a look at how to do that. So I'm going to go back here, and I'm going to create a similar like this. I'm going to create a range that is going to go from 0 to 360, and it's going to have how many steps? It's going to have 12 steps or 24 steps, for example. So that's going to be this many. And let's take a look at the values here. So I have 0, 15, 30, blah, 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 all the way down to 360. As you can see, I'm not a great fan of radians. I like working with degrees for some reason, and they're just a little more intuitive to myself. Okay, and then for this one, for each one of these, I can just do some simple arithmetic. First of all, let me set up the radius. So the radius is going to be a parameter here, and I'm going to set it at, for example, 10 units. And then what I'm going to do is of course, I'm going to use expressions. So I'm going to other expression here, and I'm going to take, for example, the angle, and this is going to be this thing here, and I'm going to take the radius as well as an input. So I'm going to take the radius, I'm going to plug it in here, and then this is going to be equal to the radius times the, what is the cosine? The cosine is cos, all right? So cosine of the angle. So that's going to be one thing. And the other one is going to be that this is going to be times the sine of the angle. But I forgot to convert the angle into radians. So I need to do that. For example, I'm going to do this here. I'm going to say that this has to be radians, and then that is what I'm going to plug into the angle. Okay, the radians are going to be here: 0, half pi, pi, 1.5, and 2 pi. Have I ever told you how I don't believe in pi? That I'm a Taoist? But I think you can actually Google that. So I won't get into that right now, okay? So I have this, and then what I can do is I can use these as the coordinates of the points. So I'm going to construct a point with this x, and you can see that this is like a squished circle right now, and with this y, and then c is going to be 0 for all of them. Okay, so that's how I would create a circle out of points. But wait, can we make this a little more exciting? What if instead of a circle we make a spiral? Can we do a spiral? Well, a spiral, instead of z being constant, what we can do is we can make c a value that increases, for example, linearly. So is, for example, let's say that I'm going to create a series that is going to start at 0. The step size is going to be 1 unit, and the count is going to be 25. I'm just going to do this manually, but you could do this, for example. Let's not do this manually, because I cannot preach things and then not do them myself. So if the steps are 24, then we need one more value here. So this should be the addition of 24 plus, the shortcut to put in a panel is 2 forward slashes. And then I can just write in here the number 1, and it will give me a panel directly with the value of 1. And then I'm going to plug that in here. So that now I have a series of numbers that start at 0, have the step size of 1, and then let's take a look at that. 0, 1, 2, all the way to 24, and then I'm going to use those to plug into the C coordinate. And then you can see I am getting a nice spiral in 3D. But wait, it's just one thingy with a spiral. Can I make the spiral like at least have a couple loops? Yes. So instead of starting at 0 and 360, I can just crank it up to 720, for example. And now I have 2 twists. And then look at this. How nice is this? Yo! All right, because the size is the same. Okie dokie. So that could be one thing. And also, wait, but the radius is kind of like a cylinder of a spiral. Do we think, what if let's double this so that we have a little bit more definition. What if we actually did something where instead of a cylinder spiral, was kind of like a cone. It started with a very small radius, and it increased that radius. Well, how do we do that? Well, instead of having the same radius for all the calculations here, we can have a radius. So instead of having the same radius for all the points, which creates a circle, if we start with a tiny radius and then we start incrementing the radius, we will basically be making a spiral in this direction. So that's why we still work with an increasing angle, but with the radius is a value that starts small and then it increases and increases and increases. How do we do that? With another series. So for example, let me say that the radius, where is my mouse? The radius, instead of being a number, just one number, is going to be a list of numbers. And so I'm going to actually copy and paste this series here. And the start is going to be 0. The step size is going to be something very small, like 0.1. And then it's going to have as many values as the steps plus 1, like we did here. And then I'm going to feed that into the radius here. And I'm going to feed that into the radius here. And then you can see now how on top it's a spiral. And the perspective here is this kind of like opening sort of cone of a spiral. I don't even know how to name this, but we can open up if we open up the step. So this can now like open up to be a bit more, and then we can just create an interpolated curve here and see this in kind of like in 3D kind of, and we could extrude something around it. We can do perpendicular planes, and we can just place ellipses, and we can do all the cool things. So let's just do that. No, we're going to place some ellipses here, you know, and then we're going to extrude that with a loft as well, and choo. Well, the loft is a little weird here, but but it's kind of I think actually the right one would be to do a sweep, with the rail being the curve and the section curves being these ones, right? I think this is a more accurate one. Yes. Okie dokie. Woohoo! So how cool is this, So we have been able to numerically define a curve by defining a sequence of points that hold some kind of relation between them. In this case, creating, for example, a spiral that is ascending in the z direction by just using simple trigonometry and like a sequence of numerical values. All right. Now, can we use this trick to generate, instead of sequences of points in one dimension or in one direction, can we do that in two directions? Like a grid of points? How would we go about that? Well, it's actually going to be fairly easy. It's just that it's going to involve a little bit of data manipulation, the way we've seen in previous videos. So for example, I have created two numerical series. One goes from 0 to 9 in increments of 1. The other one goes from 0. The other one has 5 numbers from 0 with intervals of 1.5. I want these to be the x coordinates of a grid of points, and I want these to be the y coordinates of a grid of points. So how can I do that? Well, if we were to say, let me construct a point, and then for this point, let me add the x coordinates here, and let me add the y coordinates here. What would happen is that we run into a specific behavior of grasshopper components, which is that whenever a grasshopper component takes two different lists and needs to work with them together, what it does is, if the two lists have the same branch and the same name, what it does is it tries to combine the elements from one input and from the other input. It tries to combine them one by one at the list level. So for example, what's happening here is that the component is creating the first point with 0, 0, and a c value that I haven't really specified. That is the default, but it's going to be, for example, 0 for c, okay? And then the second one is going to take the value of 1 and the 1.5, value of 2 and value of 3, value of 3 and value of 4.5, value of 4 and value of 6, and that would be this point here. But then, because Grasshopper runs out of elements on this list to match with the previous one, it just sticks to the last one. So for 5, 6, 7, 8, and 9, is going to pair those values with the last one here, with number 6. This kind of data matching is called longest list, because it basically creates element as long as the longest list, but it repeats the last one that it finds. So that's like the standard behavior for Grasshopper components. Now, this is not the behavior that I wanted. The behavior that I wanted was take coordinate 0 and then create 1 point for 0, for 1.5, for 3, forever, so that I have this point here, another, and then the second one, take coordinate 1, and then give me 1 point here, another one here, another one. So I want a 2-dimensional grid. Because Grasshopper matches elements one by one. If they belong to the same branch, then what I will need to do is that I will need to change the branches so that that one-to-one matching does not happen. So how is it going to work? Well, what I'm going to do is I'm going to open this up and I'm going to graft the tree that is coming from here, from the y coordinate. I could graph the other one, it doesn't really matter. The result of this is that I now have a data tree that looks something like this. I have 5 branches with new names. None of these names match the name of this branch, and therefore, because they are different names, a different behavior is going to happen. What's going to happen is that as I plug this here into y, now I get a 2-dimensional grid, because what happens is, since they have different names, then what the component does is it takes the whole list and it matches the elements with each one of the other lists, one by one. So it takes this whole list and it creates 1 point for each one of these elements and for each one of the elements on this branch. And because there's only one, then we get this row of points. Now for coordinate 1.5, it matches it with all these points here. We get the second row. For 3, we get the third row. For 4, for the fourth row, etc., etc. All right. So this is how you would create manually, for example, a 2-dimensional grid of points with a numerical series and doing a little bit of manipulation. Now let's say that I wanted to control where the first point is. I just don't want the grid to be here, center, and 0, 0. Let's say that I have a reference point somewhere in Rhino that I want to use as the starting point. So what I can do is I can just say, I'm going to bring that point here. I'm going to set this point. And then what I'm going to do is just a very simple operation, which is going to be, I'm going to deconstruct this. I'm going to find the x, y, z coordinates. And then what I can do is I can either add these numbers to the x direction. So to x, I'm going to add, to the x coordinate, I'm going to add all of this. And to the y coordinate, I'm going to add all of this. And then I'm going to graph this. Right? And then what happens is that now the coordinates are, and now I'm going to add this, and now the coordinates are just added to the original coordinates. So if I move this here, now things are adapting correspondingly. Alternatively, I could have just done start the series from x and from y. That could have been another, just start the series instead of from 0, start from whatever the coordinate x and the coordinate y was. It's the same thing. Actually, this is a little easier and a little more elegant to my taste. Okay. Now, can I do the same for C? Let's see if we can do that. We can actually, full disclaimer, we're not going to be able to do that because I would want to say, well, maybe we can graph this and then I'm going to plug this in here, but then guess what happens? What happens is that now I get points kind of inclined like that, just because, let me add Z here. I get points inclined like that because the structure of this grafting here is identical to what it had here. So these ones get matched to one. They don't get combined completely. So what if do I have to graft again? What if I graft again? If I graft again, we have the same problem. They get matched one-to-one. So this is not going to work. I will teach you in the next exercises, when we take a look at affine transformations, how we can use moving things around as a way of creating, for example, three-dimensional matrices as well. All right? But I think with this is where I wanted, this is as much as I wanted to talk about for numerical series and examples of how that is useful for creating, for example, sequences of points. We're going to use a lot of numerical series very soon in the practice exercises that we're going to do for this block of videos. Okay? And with that, I'm going to leave that there. And I'm going to move on to the next video, where I think we're going to take a look at Euclidean transformations. So moving things in space, scaling them, rotating them, and that kind of stuff. Until then, thank you very much for being here. This was Jose Luis. If you like this video, consider pressing the button or maybe subscribing to the channel, even turning on notifications to know when we go live and when we publish new videos, etc., etc. If you will. Okay, it's nice. It helps us keep going. So until then, thank you very much and see you on the next video. Oh, sorry. And I forgot to say, if you're interested in what you've seen in this video, you can learn more about numerical sequences and how they relate to creating points in three-dimensional space with a lecture that I gave at my Harvard Graduate School of Design course, Introduction to Computational Design. The link for that will be somewhere popping up there, or it will be in the description of the video. I don't know, somewhere. Okay? Make sure you check it out if you're interested in this topic.